Welcome to JR Industry. My name is Jonathan Nguyen. He's my partner, Raul. This is the ISA presentation for our CECS 440 Computer Architecture class for our instructor, Professor Allison.
There you go.
All right. For our agenda today, we're going over the history and logo of our company. We'll also go over the processor design, the baseline overview, enhancements we have on our ISA, any future plans we have for our ISA, and we'll have a question and answering section at the end. Our processor is called Corbinek. Our focus for Corbinek was to design a foolproof, reliable, and predictable processor. The name Corbinek is named after the castle within the Arthurian legend, which holds the Holy Grail within it, where Lancelot finds at the end. Our processor design is programmed with Verilog HDL. It's built within a RISC processor design, has a Harvard architecture, and is written in Little Indian format. The specifications we have within our Corbinek processor is a 32 64-bit integer registers, 32 64-bit floating point registers, a 32-bit instruction pointer, a 32 bits instruction registers, a 32-bit stack pointer, 32-bit memory address registers, 6 32-bit buffer registers, and a 32-bit CPSR, which holds the status flags within our processor. Here are a few here are the instruction formats of our processor. We have a triple source and floating point format. These formats, the source 1 and source 2 registers are being altered by the opcode, depending on what the opcode is, and stored into the destination registers. The double source instruction format is pretty much the same thing, but we only use one source register, altered by the opcode and stored into the destination. Single source, again, would be just a source register being altered by the opcode, which is often used for the jumps and calls. Operands for this register indirect ones, where the register are holding the jump location, call locations within the source 1 register. Conditional jumps and calls would be 24-bit sign offset, would alter the instruction pointer of the processor. And finally, the immediate operand format, which has the source 1 register altered by the opcode along with the 8-bit immediate and stored into the destination register. Okay. Here are the triple operand instructions along with their opcodes. As you can see, we have just a baseline of add, subtract, multiply, divide, and logical AND, logical OR, and logical exclusive OR. The double operand instructions along with their opcodes. The single operand instructions along with their opcodes. And conditional jumps instructions. We'll explain later in the slide what the conditions for how each jumps work. Along with the status flags, such as jump if carry only works if carry is true. Alright, and then here are the unconditional jumps, jump relative, which just use the 24-bit sign displacement, and the registers uses the source 1 destination, where the instruction pointer is altered using the source 1. And also the returns and return from interrupts commands, which returns the program back to the main function. Here are the flag processor instructions, which edits the CPSR. And then the immediate operator instructions, which uses one source register and then the 8-bit immediate hex code that follows afterwards. And the floating point instructions.
So, as you can see, we have a calculated CPI here of 4.49. We did this by simply counting the number of clock cycles it took for the certain instruction to operate. For this particular stage, we had 58 operations that took a single cycle. With fetch and decode, it ended up being 4 clock cycles for it to complete. 9 operations were 2-stage. 9 operations were 3-stage. 4 operations were 4-stage, which were the loads. And ultimately, we ended up getting a CPI of 4.49.
Mm-hmm.
So here are some of our flags that we implemented throughout our processor. We have the carry flag, which is used to signal a carry and arithmetic operations. The negative flag, which is used to denote either a negative number for the operations. Overflow, which detects overflow. 0 detects if a 0 is found after an ALU operation. And the interrupt enable, which isn't set by the ALU, it's set in the control unit in order to enable hardware interrupts by the memory unit. Here is the format for our 32-bit CPSR register. As you can see in the least significant byte, we have the overflow, followed by the 0 flag, negative carry, and then we have floating point operations, floating point flags, which is not equal, equal, less than, or equal, less than, greater than, or greater than equal. And then we made room for an additional space for enhancements in case if we ever wanted to include more flags.
Do you have any instructions that test those floating point flags, like jump if greater than?
Yeah, so majority of our jump instructions are jump if greater than.
But I mean test the actual floating point flags as opposed to the integer flags.
Oh no, these only are used to test floating point values.
But how do you test them?
We didn't include any operations that tested flags.
All of our operations just uses the regular stack carry negative 0 overflow. We actually haven't implemented any operations that uses the floating point just yet.
Also, the CPSR register gets refreshed at every clock, so the CU unit is always sending a new value based on the present state flags.
Mm-hmm.
So here are the jump conditions. So we have jump if carry, jump if not carry, jump if 0, jump if not 0, jump if negative, jump if plus. The jump if plus is actually based on 2 flags. It's based on the negative flag, and it's based on the 0 flag. Jump if overflow, jump if not overflow, jump if less than, greater than, less than or equal, below, above or equal, and so on. So the way we implemented our exchange instruction, we didn't use a temporary register. We used an XOR operation, which took 3 clock cycles to execute. Using the XOR, we take the first value in source 1 and we XOR it with the second source value. The result is then placed in the first source destination. On the second clock, we do the same. We use the same source from the previous operation and we store it to the second source. And then on the third, we XOR the second and we replace it in the first register. And ultimately the values get swapped without having to use a temporary register.
Mm-hmm. There a reason you did that?
Yeah, we wanted to go with a more hardware approach. We didn't want to have to spare a register. This is our top level diagram. As you can see, this is our central processing unit. And for this particular top level, we have 3 memory units that were used to communicate with the CPU. For the I/O unit, here we have the handshake between the interrupts, and we have the control signals, and the information, the data that is being fed into the I/O is the same that is being fed into the data memory. So whenever an interrupt occurs, data gets transferred into the I/O instead of data memory. And here is our execution unit. We have a floating point data path, an integer data path, and we have a B bus interface unit. These are the control flags that are used to communicate with the bus interface unit. Originally we had a bus tap that was used to control the control signals into each one, but as we added more instructions, we found it difficult to continue to increase the size of the bus, and we had to manually place each control signal into the bus interface unit. Here's the CPSR. The incoming signal is sign extended from a 11-bit value into a 32-bit value. Here the data memory is being multiplexed with the sign extended IR to be fed back into the integer data path. And the multiplexer is controlled using the DSLA.
Where do you do the sign extension of the 8-bit field for the immediate operands? Do you have a separate bus for that?
Yeah, it's inside the bus interface unit.
Does it come out though to the IDP? Like you show the...
Yeah, the sign extended gets extended within the BIU.
So is that one for the PC, or is that just for the immediate operands? The guy coming SC64.
This one?
Yeah.
These are for immediate values.
Okay. And for the program counter, it's internal.
Yeah.
Okay, got it.
So here you can see our bus interface unit. Yeah, there's a lot of multiplexers.
Mm-hmm.
We felt a little lonely throughout the project, so we had to add more friends in there.
We like multiplexers.
So here are 6 buffer values. An incoming 64-bit value is used to be stored in between these two 32-bit registers. They're all output enabled, load enabled. These values, the floating point and the writing buffers, which write to memory or I/O, are used on a bi-directional bus. Therefore, we needed to put these in a high impedance sinks if they're not being used. The read buffs, which only extract data, are not outputting impedance, but they are outputting zeros when they're not being used. The instruction pointer is refreshed at every cycle. Here you see a series of multiplexers, which is used for jumps. This particular branch, though, however, was used for plans of enhancements. We used this sign extended to use branch in order to execute a branch operation that would take 2 source operations and check the condition to see if it should jump on that same instruction.
Mm-hmm.
So I'll guide you to the steps of a call instruction, just to show the operation of the diagram. So on the first day of the call, we push the instruction pointer onto the right both 0 value, and we decrement the stack pointer. On the second, you can see the stack pointer has been decremented to FD again, which is all that's being done on the second clock. And on the third, the value that is in the right code 0 gets pushed into the memory, and the next instruction is calculated using a series of multiplexers here and re-pushed onto the instruction pointer. So as you can see, here's our stock block, and the instruction pointer value that is being saved onto the stack is stored in the least significant word of the stack block in memory. The higher word is not used, so it is just left with X's.
Mm-hmm.
So the call instruction and the interrupt instruction are very similar. The difference between the call and the instruction, though, and the interrupt, is that the call does not push the flags onto the memory. Instead, on the least significant word of memory, the call instruction saves IP, whereas the interrupt, the IP is stored in the most significant word, and the flags are being pushed onto the least significant word. So, for this particular processor, we weren't able to implement any future enhancements, but we did have plans. We just were too busy and we couldn't get them plans to work. As far as now, the Corvinik is capable of post and pre-increment loads. Branches and jumps were planned to be used. Even though branches are seen more on a MIPS architecture, we wanted to use it on this particular RISC architecture. The barrel shift module was ready for implementation, but we just couldn't get it to work. And we wanted to include added interrupts, such as a timer, divide by 0, and overflow. So here are the plans for our barrel shifter that we failed to implement. The output would have been stored in the high 8 bits. The source 1 would be used in bits 20 to 16. The vector unit, which would control these instructions, would be in bits 12 to 11. The shift amount would be in bits 10 to 5, and destination register would be in the last 4 bits. Barrel shifter will also allow the processor to avoid extra clocks by repeated shifts, which is why we wanted to implement it.
Mm-hmm.
And it would be doing that in one clock cycle. And we're finished our presentation, then we have time for any questions you guys might have.
On your BIU, you have a series of muxes, 2-to-1 muxes. Why did you choose to put 2-to-1 muxes instead of having a bigger mux in the bottom?
We wanted to use a more behavioral implementation of the processor. We didn't want to run into any timing issues, so we wanted to keep it simple, even if it meant more control words.
As opposed to having one, let's say, a series of 2-to-1s and one big 4 or 5-to-1.
Yeah.
How would that be a timing issue?
Well, we didn't have too much time to exercise how it would make a time difference. We just wanted to, we knew that the 2-to-1 would give us a guaranteed result. And by using a 5-to-1, we didn't want to run into any issues, last minute issues, and not having to know why.
What kind of issues?
That was delay issues for timing.
It'd actually be shorter, because it's only one path, one delay, instead of delay. Just curious. Is that what you're getting at?
Yeah.
Yeah.
So for your future enhancement for your barrel shifter, you had a destination register. So does that mean when it passes through the barrel shifter, it goes back to the register file, or does it?
It would have been in parallel. So it would have acted just like the ALU in the IDP.
Mm-hmm.
So the destination register would have been the same value that would be stored if it were being used in the ALU. So yeah, it would just go back, it would reroute and go into it.
What was the pre-ink, pre-deck, or post-deck? You said you had that kind of set up for the loads and stores?
Yeah. It would operate the same way as a load,
Yeah.
except the IDP would be implemented, and it would be used to take the source operand and either increment it by one and restore it back into the register file.
Did you start to do that and just had to pull back because of time or something?
Yeah.
Yeah, that's a pretty easy.
Yeah,
I'm
yeah.
surprised nobody else implemented something like that. Just an extra addressing mode. I don't think it costs anything.
Yeah, no, it would have been easy at
Yeah.
the time.
That's a good idea. I'm glad you showed at least what you started to work on, even though you couldn't finish it. It's always good.
Mhm.
And then you pull back when you haven't got time. That's good. Any other questions? Good job. Yeah. All right.